So today we're going to talk about modeling pumps that pump water into a reservoir and the controls that you put on pumps, and also modeling pumps that are in parallel. So where you have multiple pumps in a pump station and controlling each one individually and also calculating the flow through all of them. But to do this, I just want to introduce some basic concepts that are used as building blocks to simulate the multiple pumps. So the first thing I want to do is just show briefly building a model that has an on-off switch. And this is an important concept. It's somewhat elementary, but I still think that not enough people are using this type of concept for simulating flows into some sort of storage element in your model. So what I'll do is build a hypothetical reservoir using our new pool element. And I'll do this in metric units, megaliters and cubic meters per second as my flow. For the initial quantity, I'll put that in a data element outside of the reservoir here. Initial volume. And I'll just set this to be 500, we'll say, megaliters, and then I'll link that over into the reservoir. Like so. Okay. I also want to provide an inflow into the reservoir, and I'll do that. I don't have data handy, so I'll just use a stochastic for now. And I'll define this using a log normal distribution, and I'll just use the default 1 cubic meter per second for the mean and the standard deviation. And then I need to resample this distribution on each time step of the model. And for our purposes, just for this example, I'll assume that we have a 1-day time step for now. And so I will sample this distribution each time the elapsed day has changed. And again, if you have any trouble seeing my screen, or if I'm going too fast or whatever, just let me know. And I do welcome questions as I'm going along here. Okay, the next thing I'm going to do is just add some autocorrelation, which is just a way to make the output of the stochastic somewhat more realistic, in that the random numbers that are chosen are somewhat correlated to the previous value. Okay, so now I'll go into the reservoir inflows, and I'll create the link to the inflow that I just developed there. Now we have an inflow into the reservoir. So now I can run the model and just check things to see how it's going, and that looks about right. Okay, next thing, back to edit mode. Now I'll put in the reservoir capacity. I'll just copy and paste this initial volume and put that in there. And I'll say this is 1,000 megaliters. And I'll put that into the capacity input, upper bound, right there. Okay, next thing I want to do is put in a, and this is just a hypothetical, like I said, but it is something you would do most often in modeling reservoirs in the natural world, and that is with an elevation area or elevation storage relationship table. Water level and area. So it will result in an area of hectares and have independent units of meters. And then I'm just going to do a very simple table with 0 to 10 meters in depth that relate to 0 to 100 hectares in area, which is very large, but we'll just go ahead and go with that. And then now with this relationship, while we're simulating the volume, I can now calculate the depth and the area of the water surface in the reservoir. So we'll start here with the depth. Elevation area table reservoir, whoops. And then I have to do the table, an additional table argument to do a reverse lookup on this table. TBL, and you don't have to remember those. You can just right click here and go to constants and then table constants, and you'll see that there are these TBL constants, and the one that we're interested in here is TBL inverse integral, and that does a reverse lookup on the elevation area table. It's actually an inverse integral lookup because we are assuming that there's a linear relationship between the values and therefore can calculate the volume associated with the increments of elevation and area in this table. So it's a broad assumption, especially for a table that's so simple. In reality, you would have many more rows in this table and it'd be more accurate. But anyway, that's the way we're going to do it for this example. The next thing we want to do is calculate the area, the water surface area. Water surface area in the reservoir, and that's hectares. And so now with this lookup, it's very simple. It's just a lookup on the depth. So you put in the depth and it returns the area. Now that we have the water surface area in the pond, now we can calculate the evaporation rate. We'll just say millimeters per day, and I'll just say there's 1 millimeter per day lost due to evaporation. So now I can come back into the reservoir pool and I can go into the outflows tab and create my evaporation outflow here. And that is just a matter of multiplying the evaporation rate by the area. Now that I've created this one line item called evaporation, and this is just a name, it doesn't matter, this has no link to anything, it's just a title for this output with and then the definition of that output. Now, if I go to the outputs of the pool, you'll see, and there's an outflows folder here, and then there's the evaporation that I just created. So we can run the model, make sure it works. I do have a warning, we'll look at that later. And I'll plot the reservoir, and you can see that we've hit the capacity pretty quick. Usually, as soon as you have a capacity or you have an outflow and it hits the lower bound, you'll see that there's a message in your run log. So now I'm going to view my run log and see what that is. It says that this pool element is overflowing, but there's nothing linked to the overflow, and that's just a precaution for you to know that you have no reference anywhere to the overflow, and there's a chance that you might not be accounting for the overflow. So I'm just going to add a dummy expression here that's called overflow, just to link to that. In reality, in your model, you'll probably be sending that overflow to some other place, and so you would already be doing this. But I'm just going to, oops, reservoir dot, and now I can access all of the outputs on this reservoir by putting the dot there. Whoops, let me put that dot there again. Okay, so I want to grab the overflow, and now when I run the model, you'll see there are no warning messages. Okay, so now we have a basic model with some evaporation. I want to also add a water demand, so I'll put that over here, call this demand. And we'll put this in terms of cubic, let's say liters per second, and we'll say 1,000. I guess I could have just said 1 cubic meter per second. That'll work. Now I want to put that demand as a request on the reservoir. So I'll go back into the reservoir outflows tab, and I'll add another outflow request. This will be a second priority because evaporation is natural, it can't be controlled. Therefore, it's first priority on the outflow requests. And so to calculate this discharge, I'll say it is the water demand, like that. Okay, so the next thing we want to do is we want to add an inflow. Well, let me run the model first and let's see what it looks like. Okay, so the reservoir drains, it fills up with some inflow, but for a lot of the simulation, there's no water in the pond. So what I want to do is I want to add a pump station that delivers water into the pond to maintain some level. And the level is going to be that we want to maintain is we're going to refer to that as our target level in the pond. If I plot the depth in this model, you'll see it looks like this. It starts out at about 3 meters and then drops to 0 and is up here at 5. Up here at 5, this is where the capacity limitation is of the 1,000 cubic meters or megaliters. And so let's say that what we want to do is put in a pump station that delivers water into the pond and maintains a level of, let's say, 3 meters. Actually, let's just say 2 meters, so we're about halfway in between. So we'll build a pump that will deliver water into the pond to maintain about 2 meters in the pond. Okay, so that's a good way to simulate flows entering into a storage element, is to provide some target level. I mean, you could also do the target based on a volume. That's easier, but since I'm already calculating the depth through time, I might as well make my target a depth, since that's typically how it might be operated in the real world. First thing I'll do is create my target level. And this will be in meters, and I said 2 meters is what will be there. Let's see, I'm going to move some stuff down here. Okay, next thing I'm going to do is I'm going to specify a capacity of a pump station that pumps water into the pond. So I'll create another element here, and I'll call this pump capacity, cubic meters per second, and we'll say it has a capacity of 1. Okay, it might be tempting to just quickly add in an if statement in here that says if the depth is less than 2, then provide the pump flow, otherwise turn the pump off. And we can go ahead and see what that looks like right now. So we'll do that. I'll go into the reservoir outflow requests, and I'll put in a third line item that is, oh, I'm sorry, this is supposed to be the inflow, isn't it? So I'll go over here into the inflow, and then I'll add an item here that refers to the pump capacity. And I'll say if the depth is less than the target level, then you run the full pump capacity. Otherwise, it's going to be 0 liters per second. So you could just put an if statement in here just like this. And let's see what happens. So then we run the model, and we get this. Now, what you'll see here, so we have some oscillation going on, but we don't know the true, we don't know if this is truly the oscillation because there might be inserted time steps. Now, I can say right now that that would not be the case because we're not hitting an upper or a lower bound. But let's just say, for example, and this is what I see in a lot of models, is that rather than having a target that's above a lower bound, somebody might say, well, I'm just going to pump water into the pond if it's empty. So let's see what that looks like. So instead of saying depth is less than the target level, let's just say when the depth is let's see, let me go the other direction. Let's say if the depth is greater than 0 meters, then it's 0. Otherwise, it's the pump capacity. So what that means is, as long as there's water in the reservoir, then we don't need to do anything. But if the reservoir drains to empty, then I want you to pump water into it. So we run that, and it looks like this, but in reality, what's probably happening is it's probably oscillating more, and we can't see that unless we turn on our high resolution time history results. So let's go ahead and do that with a new time history. So I'm just going to show the current depth along with the pumping rate of inflow, which, let's see, I can't, oh yeah, so one of the outputs on the reservoir is the total inflow. I don't know, I can't isolate just the pumping inflow because I put the equation inside of the reservoir. We can look at that in a little bit. Anyway, I need to go up here to the simulation settings now, and I need to enable the high resolution time history results so that I can see everything that's happening in between my basic one-day time step. So I run the model, and now we see our oscillations near the lower bound of the reservoir. And the reason for this is that GoldSim inserts a time step every time the reservoir is at its lower bound, which can happen in between, well, which would likely happen between time steps. So that is some logic you would need to be careful of to not do that. And if we go ahead and rather than use the lower bound as the target, instead we use the target level, which is above the lower bound, you'll see it will be a little bit different. So I'll go ahead and say that now. If the current depth is larger or higher than the target level, then we don't need to pump, otherwise we will. Run the model, and now what you'll see is that we don't have as many oscillations because we're not inserting time steps every time we hit the lower bound. However, in a more complex model, you may be inserting time steps for other reasons at other places, at other reservoirs, for example, and that would cause these oscillations to be tighter because you would be updating its values more often. You might also have in your model the ability to insert time steps turned off, which happens a lot in models. So you might not even have this checkbox checked here, and then you wouldn't be inserting any time steps. But still, I'm not sure I'm a fan of this, the way that this reservoir is operating currently, where it's turning on and off every day, like this. So, and you might have smaller time steps, right, where it's oscillating even at a faster rate. So the preferred way here is to use a status element. So I'm going up here to insert an event element, and it's called the status element. This is an excellent way to simulate water being pumped into or out of a pond in order to maintain a level. So I'll call this the pump status. And now what I want to do here is I want to turn the pump on when we are slightly above the target level. So I'll go here to true, and I'll say when the depth is greater than the target level, and then I'm just going to multiply a small fractional increase to this, 1.1 we'll say, so 10% above the target level. Then we will, sorry, I'm going backwards here. We turn the pump on. This is an inflow. So when we turn the pump on, it's when we are less than the target level. And I'm going to go slightly below the target level. Okay, so we're going to wait to turn the pump on until we're below the target level by 10% lower than the target level. And then we will turn the pump off. We're going to wait to turn the pump off until we are above the target level by 1.1 times the target level above it. Okay, so now with this pump status, now I can go back in here to my inflow, and instead of saying if depth is greater than this, we just change this whole condition right here to be referencing our pump status right there. So if the pump status is true, then it will be pumping. So I need to switch this around. Otherwise, it will be 0. like that. Another way to do this, instead of calling this pump status, is you could say pump on, true if on, false if off, something like that. That way it reads a little bit better. So when you go look at this equation, it says if the pump is on, then flow at the pump capacity, otherwise 0. So that makes a little bit more logical sense there. So now when we run the model, we can see that we're not oscillating nearly as much here. So the pump, and you see that the depth is rising above 2 meters, then it shuts off, and it allows us to drop down below the 2 meter mark before it turns back on and starts to rise again. Okay, so this is a safe way, this is a good, robust way to simulate flows into the pond, or also you might have flows or a pump discharging water from the pond, but using the status element is definitely the way to go. You might also have a lookup table that acts sort of like a rating curve that as you as your water level rises above a target, you gradually increase your flows using a lookup table. You could do that too. Okay, the next thing I want to show you is a script element that is used to calculate flows in a pump that have a head relationship to the flow rate. So let's see. Here's a model here. And by the way, these models can be downloaded from our website library. Let me show you where they are. If you go to our website, go to the library, and then you could just search by pump if you wanted to. And there is, so the parallel flow, oh no, that's not the one, I'm sorry. Okay. You want to go to applications and then hydraulics. Okay, so flow in a, I'm sorry, that's still the same one. Pumping head problem. Okay, so that's the one that we're just going to look at right now. Parallel pumps is what we're also going to look at. And I'll provide these along with the recording of the webinar as well. The other one that we just did is going to be located in the reservoirs category, and it is called controlling reservoir discharge. So that's the other one that you'll want to look at. That's what we just covered. Okay, so in this model, what we're doing is we're saying we're pumping water into this reservoir, but the water has to flow through a long pipeline. And the higher the flow rate, the greater the head losses through the pipe. And so this is an equation, or this is a problem that requires an iterative solution. And so in this case, we're using a script element to do a binary search. You could also, any kind of zero root finder type algorithm like Newton-Raphson or secant method, or like this, in this case, binary search, would be useful, or would give you the ability to solve this kind of problem where you need to know the head loss, and the head loss affects the flow, which is also affecting the head loss. So this kind of problem, requires an iterative solution. And this, again, like I said, is on our website to be downloaded. And so what this model does is we have a water level, and that is impacting how much water can flow through this pump, but also the friction losses in the pipe as the water flows from the pump to the reservoir also contribute to how much water can be pumped there. And so the way it works is we have a pump curve using a lookup table that looks like this. And what this says is, as the head loss, or not just the head loss, but the total head exerted on the pump station, as that increases, then the resulting flow out of the pump decreases. And this is information that you would get from the manufacturer of the pump. Okay, so with that pump curve, you also have some data to define the pipe itself that where the water flows from the pump to the reservoir. So you have its length and diameter and some friction factor. In this case, we're using Hazen-Williams equation for head loss in a pipeline, but you could use other equations as well instead of that if you wanted. During the simulation, we need to calculate the flow area in the pipe, the wetted perimeter, and the hydraulic radius. Now, these are all constants. We're assuming that the pipe is always full. Okay, so now what we need to do is look at the script itself, and in here what we have is we start out with guesses. We start out with a high guess flow of 10,000 CFS. I just picked some really big number that it would never be greater than that. So and then the low value is 0. And then what we do is we start the binary search in a while loop. So in a script element, you can just go in here to insert, and you can pick different types of loops. Before, do a repeat until a while, and this is just a while loop. So while we're not converged, and converged is an input that, or a variable in this model that has an initial value of false. So that means it will not be going, it's got a not here, so not converged. While not converged, then we continue to loop through this until the converged value becomes true. Okay, so then what we do is we start with our mid being calculated here. It's just part of that equation. Then we go in and we say, okay, what is the head loss based on that mid flow? So we're going right into the center between our high guess and our low guess, and we're saying, okay, based on that middle value, here is the head loss. Based on that head loss, here is the flow, the resulting flow, based on the pump curve. Then we come into the rest of the, this is the rest of the binary search algorithm part right here, where we say, okay, if the result is less than the mid, then switch the high in the mid, otherwise switch the low in the mid, and the convergence is here, and then you continue to loop through that until finally the mid is, or the low and the high values are almost equal. And you can see they're about equal within 0.01 CFS. That's our convergence criteria. I'm just going to put a space around this subtraction. It's easier to read. Okay. And then, of course, we can calculate the total dynamic head as the head loss plus the water level in the reservoir. And this is just another variable in the script, but you can define it as, or you can expose it as an output on the script here. So now if you look at the script outputs, you'll see that we have the main output, which is pump flow. That's the same name as the script itself. And then any additional outputs that we've added by exposing them, like the total dynamic head, TDH, here. Okay, so when we run this model, what we see here is that, in fact, I'm going to instead of showing just the volume compared to the pump flow, I'm going to show the total dynamic head versus the pump flow. So I'm going to switch out the volume here with the total dynamic head, TDH. And now you can see that this relationship is based on that lookup table right here, where the total head on the pump is, when it's going up, then our flow is correspondingly going down. So they're opposites, as you can see here. But the flow rate being exerted by the pump, you can see varies quite a bit in this case because of the pump curve. And that's why it would be important in a model like this to simulate the pump this way. Sometimes you can just simplify it. I mean, if it's a large time step, you could just say, well, we're going to ignore head losses and just say that it's, the flow is just some constant, and ignore these kinds of details. But in some cases, the flow can vary quite widely. In this case, it's more than double. The flow rate is varying, from all the way from 5 all the way up to 18 CFS there, just based on the variation in the head. Okay, so what you can do is combine the two concepts that we just covered. You can use both the script element to calculate the flow, and then also turn it on and off based on using the status element that we just looked at. So that would just be a matter of providing a target here. Let's say you said, oh, I want, well, now I need to look at the water level. So let me change the total dynamic head with the water level. You might want to say my reservoir target is, 70 feet or something like that. And then the reservoir or the pump station would then shut off as soon as the water level hit that 70-foot mark. So instead of seeing the flow continuing at this point, you would see it just shuts off right there, for example. Okay, so now let's talk about parallel pumps. And this is a bit more tricky, but you need to know all of the things we just talked about in order to get to that point. Okay, so here is another model that I need to move this stuff up here. Okay, so in this model, oh, did I not move it? There we go. Okay, in this model, what we have, I'm going to scroll down just a bit here. I have this little diagram that shows combinations of pumps that are pumping water into a pond or into a tank in this case. Let me just go up a level so you can see a diagram. Okay, so we have some source of water, and water's being pumped from this tank through a combination of 3 pumps up to another tank. And the pumps are not the same size. And so you want to choose a combination of pumps in order to get the correct flow or deliver water the most efficiently up to this other tank. And we're going to use the water level in the upstream tank to drive which pumps we have turned on at the pump station. There's another way you could simulate this. You could say, I just want a set target flow rate, and then you just tell me which combination of pumps to get that flow rate. And that'd be a different kind of problem. In this problem, we're saying, I don't know what the flow is. All I need to know is I need to maintain a water level up here. And so I'm going to calculate, or GoldSim's going to calculate the flow rate, and also select the various pumps to have turned on in order to achieve that flow that's needed to maintain the level. Okay, so to do that, we need a combination of things. We need what we just talked about. We need the switch elements, or the status elements that we just talked about. We're going to have multiple status elements because we have multiple pumps. We're also going to need that script element that calculates the flow, the corresponding flow based on the head exerted, or the head being applied on the pump itself. Okay, so let's first talk about the basic concept of choosing the pumps. So if you look at this graphic down here, what you'll see is that we have the levels going from the bottom of the tank up to the top of the tank at 20 feet, and then increments in between. And if our water level is above 16 feet, then we don't want to be pumping any water up there. We'll just let it float, and everything will be shut off. As soon as, and by the way, this black line is based on the last simulation I just ran, the water level that was being calculated. And just FYI, so you know how to do this in the future, when you look at a time history chart, you can export the values or the lines as a vector drawing. So and that's what I did in this case, is I just said, and is that the same plot line? I guess it is. I just right-click in the plot and select export, and it becomes an EMF file, which can then be imported into, let's say, PowerPoint, and then you can explode it and just take whatever you want from that drawing. And that's how I got this line right here, is I just copied and pasted it back in from PowerPoint after ungrouping the vector drawing. So then you have individual components of that chart that you can work with. So it's kind of nice. Actually, let me just show you that really quick, how you do it. So I go in here, export, and I'm just going to put this on my desktop here, and I'll call it plot 1. And notice it's EMF. That's how I want it. Okay, I exported that thing. Now I'm going into PowerPoint. And then I go up here to insert pictures, and then I go to my desktop and I put in the plot. And what you'll see is immediately it's just one solid image that's all together, but I want to ungroup the individual components of this chart. So I will go over here to right click and group and ungroup. And as soon as you do this, PowerPoint is going to ask you if this image needs to be converted, which it does. It needs to be converted to a Microsoft Office drawing object. So I say yes, now it is converted. Can't really tell, I mean, nothing's really changed, but now I can ungroup. So I go over here to ungroup, and now I have individual components. You can see I can, let me get rid of this stuff over here. Okay, and now I can zoom in, and now you can see I have individual components. In fact, I could change numbers here. I could say, 22 there. I mean, these are all individual components now. But the line is what I want. So I could go here and say Control X to grab that and put it on the clipboard. I could grab everything, delete it, and then paste, and there's my line. And so this is the line that I copied and pasted back into GoldSim. Just FYI. Okay, so when the water level drops down out of the no pump zone and into the zone of 14 to 16 feet, then we're going to turn on pump 1. So I have 3 pumps. I'm just going to turn on pump 1. And if the water level continues to draw down and that's not enough water that we're pumping, it might go into this third zone where we need to turn on a second pump. And we'll do that until if we drop down into this third zone, we'll turn on the second and third pumps. It turns out pump 1 is a smaller pump. 2 and 3 are larger ones, so having 2 and 3 turned on is going to be more flow than having 1 and 2 turned on, just so you know. It's just one way to do it. It depends on the sizes of your pumps. Then if it continues to drop and it's down into this lower zone, then you would turn all 3 pumps on. Okay, so now let's look at the script and how we walk through those different combinations of pumps. So this is the same exact binary search algorithm that we were just looking at with some additional if statements to determine which criteria we're in or which zone that we're currently looking at. So the first if statement says, okay, if switch 4, then what that means is that we're all the way down in the critical zone and we need all 3 pumps turned on, and the resulting flow is going to be the flow of pump 1, 2, and 3. Okay, and the way that we've calculated these pump flows, pump 1, pump 2, and pump 3, is that it's looking at, and that's just defined above that in the previous 3 lines, and that is looking at these pump curves. So just to review these pump curves, these are the curves that I mentioned you can get from the pump manufacturer, and if you look at that, you'll see it similar to what we saw before. There's varying head, and that has a resulting varying flow that diminishes as the head is increasing on the pump. Okay, so in this if statement here in the script, then what we're going to do is look at calculating the pump in all 3 of the pump stations because we are down in the critical zone. Therefore, we want to turn on all 3 pumps. And you're probably asking, well, how do we know we're in this critical zone? It's because we have this if statement that says if pump switch 4, which is my switch element. And so let me go back to the switch element. The switch element is over here saying that we are in pump switch 4. This is true if the reservoir depth is less than our critical trigger, which is down there at like 7 feet. That's the critical trigger depth. We turn it off if we're above the critical depth with a little bit of leeway. That's this dead band. The dead band I just put in there as a 2 foot, give or take a little bit so that we don't oscillate so much. Okay, going back into the script element here, we just walk through each of these categories. If we're in switch 3, then, and I have to put in not switch 4 because there's a situation where you could be in both. So I want to make sure that we're, one's true, one's shut off before we go into the next zone because of the dead band. Okay, so if we're in the zone, if we're in this yellow zone, essentially, then turn on pump 3 and 2, but make sure 1 is off. So that's what we had specified here. Let me scoot this over so you can see it's just 2 and 3 right there. Okay, so we've defined those flows, and now we can calculate the resulting flow, which is 1, 2, and 3 again. I probably didn't need to add 1 in there because it's a 0, but anyway, that's just pumps 2 and 3. And then we go into the next if statement, and oh, and you know what? I think I need to change this a bit. I had this output that was telling you how many pumps were running. This should say 3 pumps. We only have 3 pumps. And then this one should say 2 pumps. I think the original model, this is correct. I just changed this yesterday. 2, 2. Okay, so this output number of pumps, it just tells you, yeah, how many pumps are running currently. And I think I just had that defined because I had a dashboard that would show a little bar symbol that increased, just to show you generally how many pumps are running during the simulation. I don't think I'm using it in any other place. It was just in a dashboard, which I've deleted, so it's not really used. But anyway, so we walk through these if statements, and finally you get to the point where it says, okay, if we're in pump switch 1, that means that's the blue zone up here, and we only have 1 pump running. And then end the if statement. Otherwise, none of these will be true, and you will have a result of no flow. And then we finish our bisection method here and calculate a convergence and that will stop the looping. But you can see that this is exactly the same logic we had before in our script element. It just adds the one little bit of these if statements here to determine which combinations of pumps we're using, but we're still calculating the flow the same way by using the total dynamic head being applied to all the pumps, which is the same for all the pumps because they are operating in parallel. So that's the key, because they're operating in parallel. Okay, so we can still calculate the power being exerted by all 3 of the pumps the same way we do it with the single pump, in that we have you might have efficiency tables for your pumps, which also would come from the manufacturer, but that you can calculate the power, which we don't need to get into how we're doing it, but anyway, it just has to do with the flow and the efficiency. It's just this is just the horsepower equation here. So then you can just sum the 3 up from these 3 pumps, and then you have the total power in horsepower, and then you can calculate the total energy in megawatt hours, for example, during the simulation. Okay, so then the same thing, we just have a tank up here, very similar to what we had before. This is very simple, but essentially all we're doing is just saying we have some water depth that contributes to the total dynamic head on the pump, and then we're going to monitor that through time, and this is the main control point that's telling us which pumps to turn on, and the head losses through the pipe, of course. But now when we run this model, we can see that the pumps are turning on at different amounts. So at the beginning of the simulation, actually, let me go back to this other graphic here so you can kind of see at the same time what's going on. Does this show all the pumps? Yes. Okay, so you can see at the beginning of the simulation, our water level is at about 9 feet. So because we're at 9 feet, we should have 2 pumps turned on. We do. We have pumps 2 and 3 because we are down here in this yellow zone here. So we have pumps 2 and 3 turned on. And you can see that pump 3 is a much larger pump than pump 2. So then the water draws up into this green zone, and now we have pumps 1 and 2 turned on. Well, green is the 1 and blue is 2. And you can see those are both smaller pumps. Also, you can see that the water flow here in the blue line is slowly drawing down, and that's corresponding to a water level that is increasing. Also, while the large pump, number 3, while that's running, it's a much higher flow rate, therefore the head losses are greater in the pipe, therefore the flow that you see coming out of pump 2 is lower, while there's more flow going through the pipe. Then as soon as that as soon as the large pump turns off, then the flow in pump 2 suddenly increases because the flow has dropped down. The total flow in the pipe has dropped down. Therefore, you can see the immediate effects of head losses in this regime here. So that's why it's important. I mean, it's not a huge difference. It's only a difference of maybe a CFS or so, but it could matter in the long run in your model. Okay, then we get to a point where we've risen up into this blue zone. Therefore, we only have the single one pump turned on. Then we go up into a point where it's high enough, we don't need any pumps turned on, they all shut off. And then you finally get over here into this zone where the water draws way down, and you can see we have all 3 pumps turned on. We have pump 1, pump 2, and pump 3 all turned on. And you can see again the effects of the head losses in the overall flow rate as soon as all 3 pumps turn on. You can see this drops down up there. Okay, so this is one way to simulate pumps in parallel, but like I said, you might have a situation where you need to just have a constant flow rate, and then you just want GoldSim to just tell you, based on that flow, what pumps are currently being turned on. And that would just be a simple calculation. You wouldn't need to do this big while loop and the script element and all that to do that kind of a calculation. But I would say this is probably more common where you're trying to maintain a level upstream or downstream. Maybe you're pumping water out of something, but it'd be very similar, whether it's in or going out of the reservoir. So that is pretty much all I wanted to show you in this model. I hope this was useful for you. And like I said, these models, all 3 of these models are available in our library. If you have questions about where they are, you can't find them, please let us know. And I hope to see you next month at our next webinar, which is, we just updated our schedule. So next month is a fracking water life cycle analysis model that's based on a similar model that was developed by a consulting firm in a spreadsheet. And this has been built in GoldSim, and it would be just kind of walking through that model there. So anyway, thanks for joining, and I will field any questions that you have at this time. Okay, so somebody asked, what is the purpose of using these combinations? I'm assuming of the pumps that you're talking about, so let me go back to that model. Okay, so what is the purpose of using these combinations of pumps as opposed to some other combination? The purpose is really based on flow. So in this case, we have 2 small pumps, 1 and 2, and then a very large pump. And so, yeah, to be more efficient, we would use the smaller pumps when we only need a small amount of flow to essentially top off the tank. But we don't want to turn on and off this big pump very often. And in reality, what you might have is what's called a variable speed pump that can be ramped up and down, and then you would only turn on and off the very large pumps that might be constant speed, only when you absolutely have to. There might be things like demand charges that power companies charge. For example, they might do that every time the big pump is turned on, and you get an extra charge on your bill every single time that happens. And so you would want to minimize the number of times that the big pump's turned on and off. And so then that would be an excellent case in this model where you'd want to only turn it on when you're down in the critical zone of this level, in the orange zone in this image. And so that would kind of determine how and when you want to turn those on. But sometimes, so I built a model similar to this for a real project, and it turned out that just in building the model, we found that there were certain things that the designers at the pump station didn't consider in the operation. For example, we found that based on the way they wanted to operate it, there was one pump that would be turned on way more than all of the others, and it would burn out faster than the others. And so we determined that using a combination of pumps in which you spread out the load on the other pumps would make the whole pump station last longer. And so it was just actually happened through just I don't know if I would say, yeah, I'd say trial and error, and just building the model and just seeing how the combinations worked over time, and we were able to just see that by uh, playing with these combinations of pumps, and before they actually set that in stone and were operating it in the real world. So I guess I would say it's a combination of efficiency and how long the load, I guess the load on the pumps, how what's the wear and tear on the pumps over time. That was also a determining factor. Okay, I'm going to wait around for any other questions, but for now I will stop the recording, and thank you for joining us, and see you next month.